Here's our second problem as an example for vectors. This one, we're specifically talking about displacement vectors. So reading through this, we have an airplane going through the following displacements. It flies 66 kilometers. So I would draw a vector that represents 66 kilometers. And they give us a direction of 30 degrees east of north. When we are talking about north, south, east, west, we typically superimpose north as the positive y direction, south as the negative y direction, east positive x, west negative x. When this problem says in a direction 30 degrees east of north, that means I want to draw a line representing north, and the angle is eastward from north by that 30 degrees. From there, our airplane flies 40 kilometers due south. I can draw that, as I write my vectors out, I like to draw them separately. So our second vector, 49 kilometers due south. Finally, it flies 100 kilometers, 30 degrees north of west. That means we draw west and go north of it by 30 degrees. Now, we could draw a rough sketch saying, okay, this way, then this way, then this way. Our answer should look something like this, our result, because it's asking us how far and in what direction the airplane ends up. But this, to me, is total chaos. So it's totally good to have a rough idea of what the answer should look like. But when I don't draw to scale, which I'm not, I find my drawing them head to tail every single time leads me to more of a mess than anything helpful. What I do remember, though, if we were to call this vector A, this vector B, this vector C, if we're trying to find out overall how far the airplane ends up from its starting point and the direction, we're essentially saying what is the resultant vector, where do we end up, once we have accounted for these three legs of the trip, for leg A, B, and C. So, similar to other examples, we can say the overall x component, where the airplane ends up, east or west, depends upon how far it traveled east originally. Technically, it doesn't travel east or west during that vector B portion, but I'm still going to write it out. We'll put in the 0. And then it will also be determined by how far west the plane travels during leg C. And then similarly, the y component will be found by adding these y components together. So the approach to these vector problems, when we're just ultimately trying to add a bunch of vectors together, we want to find the x and y components of the individual vectors and then add all the x components together to get an x component answer, add all the y components together to get a y component answer. So going back to vector A, I'm going to draw this one because I know the 30 degrees is up here. I'm going to draw my y component first and my x component second. For the y component, I had to go upwards, so that's a positive y component. Then I had to go to the right. That's a positive x component. There's our right angle up there where the x and y components meet. This one, notice this x component up here is actually opposite the 30 degrees. The function we have that includes opposite and hypotenuse is sine. We can say that the sine of 30 degrees in this case, because of our triangle, is going to equal AX over 66. I'm just going to leave the units in kilometers because they're all in kilometers, and that will give me an answer in kilometers. What we can say here is that AX points to the right, so positive, a distance of whatever 66 sine 30 gives us. In the previous example, we've had cosine being for the x direction, and that's totally true if we have measured our angle from the x-axis. If we wanted to draw AX over here, we would need to use the 60-degree angle. And we would say 66 cosine of 30, which gives us the same number as 66 sine 30. It's good to draw the triangles just to make sure we're totally confident in sine versus cosine. The y component, using my original triangle, the y component is adjacent to the 30 degrees. So we're going to end up with 66 cosine 30. But similarly, you can totally draw the y component over here and do 66 sine 60. They give us the same numbers. We do know this is positive as well. We don't have to draw the positive sign, but it is always good to make sure you're thinking that direction step through. Vector B, the x component we can see is 0. We don't go east or west at all. The y component is down to 49 kilometers. Vector C, we can see drawing the x component in, we go to the left, and then drawing the y component in, we go up. So the x component is going to be negative, the y component is going to be positive. Looking in this triangle, this x component here is adjacent to this angle of 30 degrees. So we want cosine. We'll have 100 kilometers times the cosine of 30. And just as a reminder, that comes by saying the cosine of 30 is the adjacent side over the hypotenuse. So we can say this x component points to the left, negative, and then 100 cosine 30. The y component being opposite will be 100 sine 30. To make this into an equation that is going to answer this question of how far the airplane ends up from its starting point, the resulting x component, we're going to take how far east the plane moves during the first step, plus how far it moves during the second step. So I'm writing the 0 just so we're aware that we're accounting, we're thinking about all three vectors. And then plus how far it moves, in this case to the left or to the west in the third step. So we're just adding these x components together. I'll just plug it in. I'm getting negative 53.60. This will be kilometers. Because I'm not at a final answer, that's why I'm keeping a few decimal places. Our other component, the y component, we're essentially setting up the similar equation just with y components overall. So in the y direction, we're accounting for how far north the plane flies first, and then how far south it flies, and then how far north it flies again. So north for the first step, south for the second step, north for the third step. getting 58.16 kilometers. So this answer at the moment is telling us the airplane ends up, if this was his starting point, this dot, this airplane ends up to the left by 53.6 kilometers and north by 58.16 kilometers. The question is specifically asking us how far and in what direction. That means just straight line. If this airplane were to fly in a straight line from starting point to ending point, how far would this be? So how far? What direction means what angle? What angle would this airplane have to head in to get to that place? So how far? The length of the vector is this Pythagorean theorem. So 58.16 squared plus 53.60 squared. So 79 kilometers. We can say that the tangent of that angle is the opposite side over the adjacent side. So if we take the inverse tangent of both sides, we get 47 degrees. What we would want to say, we could either go all the way from positive x over, but with the wording of the problem, east of north or north of west, it would definitely make sense to say 47 degrees north of west. Meaning, if we draw in west, which is to the left, and go north by 47 degrees, that is the direction the plane would need to fly in. So this is our answer right here.